For the longest time, the idea of gaming on Linux sounded like a punchline. If you were a PC gamer in the early 2000s or 2010s, Linux was for servers, coding, or tinkering, not for launching the latest AAA title. You dual-booted into Windows for anything serious. Performance was inconsistent, driver support fragile, anti-cheat systems refused to cooperate. Most major studios didn't even acknowledge Linux as a platform worth targeting. Fast forward to now, and something dramatic has changed. Linux is no longer a curiosity. It is no longer a desperate workaround. It's a legitimate, stable, high-performance gaming platform. So what happened? Why is Linux now so good at gaming? The answer isn't a single breakthrough. It's a convergence of technologies, corporate strategy shifts, and driver maturity. Graphics API evolution, community engineering, and one very important catalyst, Valve's investment in Linux. But to understand why Linux gaming is strong today, we need to understand why it used to be weak. Historically, the biggest barrier was the graphics stack. Windows gaming revolved around DirectX. Microsoft's proprietary graphics API tightly integrated with Windows. Game engines were built around Direct 3D. Developers optimized specifically for that environment. Linux, on the other hand, relied on OpenGL. While OpenGL was powerful, driver implementations were inconsistent across vendors. Performance optimization on Linux often lagged behind Windows because GPU manufacturers prioritized Windows drivers. When your entire gaming ecosystem is optimized for DirectX and your platform uses something else, you start from a disadvantage. The next issue was market share. Developers follow money. Linux desktop market share remained small. Publishers saw little financial incentive to allocate development resources toward native ports. Some studios experimented with Linux builds, but maintaining a separate platform required QA, packaging, support, and driver coordination. Most publishers decided it wasn't worth it. Then came the inflection point. In 2013, Valve announced SteamOS, a Linux-based operating system designed for gaming. At the time, it seemed ambitious but unrealistic. The initial Steam Machines experiment didn't dominate the market, but the strategic direction mattered. Valve wasn't just shipping an operating system. They were building infrastructure. The real revolution began with the development of Proton, Valve's compatibility layer built on top of Wine. Wine had existed for years, allowing Windows applications to run on Linux by translating Windows API calls into POSIX-compatible equivalents. But Wine alone wasn't enough for high-performance gaming. What Proton did was integrate Wine with additional technologies like DXVK and later VKD3D. DXVK translates direct 3D 9, 10, and 11 calls into Vulkan. VKD3D translates direct 3D 12 into Vulkan. Vulkan, unlike OpenGL, is a modern low-overhead graphics API designed for high efficiency and cross-platform compatibility. This translation layer changed everything. Instead of developers needing to create native Linux ports, Proton allowed Windows games to run on Linux, with minimal developer involvement. More importantly, Vulkan's low-level design meant that translated DirectX calls could perform surprisingly close to native speeds. In some cases, performance matched Windows. In a few edge cases, it even exceeded it due to differences in driver overhead. Driver maturity is another crucial piece of the puzzle. Over the past decade, Linux graphics drivers have improved dramatically. NVIDIA, once criticized for weak Linux support, now provides consistent driver updates aligned with major game releases. AMD embraced open-source driver development, contributing heavily to the Mesa project. Intel improved its integrated GPU stack. The Mesa driver ecosystem, particularly for AMD GPUs, matured into a high-performance, stable graphics foundation. Open-source drivers are now often deeply optimized and closely integrated with the Linux kernel, reducing latency and improving compatibility. Another critical factor is shader compilation and caching. Early Linux gaming suffered from stutter caused by shader compilation happening during gameplay. Proton introduced shader pre-caching mechanisms integrated with Steam. When players launch a game, shaders are often compiled ahead of time, or downloaded as pre-built caches. This reduces runtime stutter and makes gameplay smoother. Valve also implemented background processing systems that optimize shader compilation during idle periods. Anti-cheat compatibility used to be a deal breaker. Multiplayer games relying on kernel-level anti-cheat systems simply refused to run. This locked Linux gamers out of major competitive titles. Over time, Valve worked with anti-cheat vendors to enable Proton compatibility. Today, many multiplayer games enable Linux support by toggling compatibility flags on their back-end systems. This doesn't cover every title, but the list of supported multiplayer games has grown substantially. The Steam Deck represents perhaps the most visible validation of Linux gaming's maturity. Valve shipped a handheld gaming device powered by a custom Linux distribution. The device runs thousands of Windows games through Proton seamlessly. For a company to build its flagship hardware around Linux, it had to ensure compatibility at scale. That meant aggressive testing, developer outreach, and continuous Proton updates. The Steam Deck forced Linux gaming into mainstream awareness. Game engines also evolved. Modern engines like Unity and Unreal Engine support Vulkan natively. When a developer builds a game using Vulkan, Linux support becomes far easier. Even when games ship primarily targeting Windows, Vulkan support simplifies compatibility. Cross-platform engines reduce reliance on DirectX-only features and lower the barrier to Linux support. The rise of Vulkan itself deserves special emphasis. Vulkan is designed for explicit control, lower CPU overhead, and multi-threaded efficiency. Because it's cross-platform, developers can target it without being locked into Windows. Proton leverages Vulkan as the bridge between DirectX and Linux graphics drivers. Without Vulkan, translation would be far less efficient. Kernel improvements have also contributed. The Linux kernel now includes features like improved CPU scheduler behavior for gaming workloads. Technologies like FSYNC and async optimize synchronization primitives in Wine, reducing overhead and improving frame pacing. These low-level changes matter in performance-sensitive scenarios. Another major shift is storage performance. Linux file systems like Extension 4 and BTRFS, combined with modern NVMe drives, provide excellent throughput and low latency. While Windows also performs well, Linux's flexibility in file system tuning allows advanced users to optimize their systems for gaming workloads. Community involvement cannot be overstated. Linux gaming improvements are not solely corporate-driven. Community developers contribute patches, test compatibility, maintain compatibility databases, and report regressions. This collaborative ecosystem accelerates problem resolution. There's also the matter of system overhead. Linux distributions often run with fewer background services compared to a default Windows installation. While modern Windows is optimized for performance, it includes telemetry, indexing, and background tasks that consume resources. On equivalent hardware, Linux can sometimes offer slightly lower idle CPU and RAM usage, freeing resources for games. Input latency improvements further strengthen Linux gaming. Wayland compositors and optimized display pipelines reduce input lag. High refresh rate monitor support, variable refresh rate technologies like AMD FreeSync, and low latency kernel configurations contribute to competitive viability. Another overlooked aspect is containerization and sandboxing. Tools like Flatpak enable consistent runtime environments, reducing dependency conflicts. While gaming typically relies on Steam's runtime, the broader Linux ecosystem benefits from containerized software deployment, increasing stability. Modding support has also improved. Many Windows games rely on mod loaders and file injections. Proton has matured to handle many of these cases. While not every mod works flawlessly, compatibility has expanded significantly. Hardware support beyond GPUs matters too. Game controllers, VR headsets, and audio devices receive better Linux support today than ever before. Kernel drivers recognize Xbox and PlayStation controllers natively. Bluetooth stack stability has improved. VR platforms have experimental Linux compatibility pathways. Cloud integration is another dimension. Cross-save systems, cloud storage, and multiplayer backends operate independently of operating system. As gaming shifts toward cloud-connected ecosystems, the OS becomes less central to compatibility decisions. Economic incentives also shifted. Microsoft's ecosystem control through Windows remains strong, but Valve recognized the strategic risk of relying entirely on a competitor's platform. By investing in Linux, Valve ensured independence. That investment translated into tangible improvements for end users. Performance benchmarking consistently shows that many games now run within single-digit percentage differences compared to Windows. In GPU-bound scenarios, translation overhead is minimal. CPU-bound scenarios may show slightly larger deltas, but kernel and driver optimizations continue narrowing the gap. There are still limitations. Not every game runs flawlessly. certain anti-cheat systems remain incompatible. Some launchers require workarounds, but the difference today is scale. Thousands of games work. The percentage of compatible titles grows regularly. The psychological barrier has shifted too. Developers and gamers now view Linux as viable. That perception encourages more developers to test compatibility. When a developer toggles a compatibility flag enabling Proton support, they instantly expand their audience. The open source model accelerates innovation. When performance issues arise, developers can analyze logs, patch components, and distribute fixes quickly. The transparency of the Linux ecosystem fosters rapid iteration. Another key factor is the decoupling of gaming ARPAs from operating systems. As Vulkan adoption grows and DirectX to Vulkan translation improves, the underlying OS matters less. Graphics calls become portable. Steam shader precaching infrastructure and compatibility database represent industrial-scale engineering solutions layered on top of community-driven foundations. This hybrid approach combines corporate resources with open-source collaboration. Modern Linux distributions simplify setup. Installing GPU drivers is often straightforward. Enabling Proton requires minimal configuration. Gaming on Linux no longer demands deep terminal expertise. The narrative has changed from "Can Linux run games?" to "Why wouldn't it?" That shift reflects measurable technical progress. In summary, Linux is now so good at gaming because the entire stack evolved simultaneously. Proton translated compatibility from theory into practical reality. Vulkan provided a high-performance cross-platform graphics foundation. GPU drivers matured dramatically. Anti-cheat vendors enabled support pathways. The Steam Deck validated large-scale deployment. Kernel optimizations improved synchronization and latency. Community contributions accelerated testing and fixes. Game engines embraced cross-platform ARPAs. And corporate strategy aligned incentives with independence. Linux didn't magically become good at gaming overnight. It became good because engineers attacked every bottleneck systematically. Translation overhead was reduced. Driver gaps were closed. API inefficiencies were minimized. User experience was streamlined. The ecosystem matured. Today, choosing Linux for gaming is no longer an act of rebellion. It's a rational decision supported by data, engineering progress, and an ecosystem that finally reached critical mass. The question is no longer why Linux gaming works. The real question is how much further it will go from here.